Swayam Prabha. Digital India. Educated India.
This is what we are discussing, and if you recall the last at the end we are talking about the solution by increasing your sample size, because after all, as we discussed yesterday, that multicollinearity is mostly a sample problem. And what basically happens if you increase the sample size? If you look at the variance of beta hat j equals to sigma square divided by summation x j square into 1 minus r square j, right. So, that means this we can say that sigma square divided by summation x j square into 1 by 1 minus r square j. There are two components, and in presence of multicollinearity, what happens? This is actually your variance inflating factor, if you recall, 1 by 1 minus r square j. So, this variance inflating factor in presence of multicollinearity, that will give you some upward shock in the variance, right. Okay, this variance inflating factor. But if you increase the sample size, the summation x j square, which is nothing but sum of x j minus x j bar whole square. So, generally as you increase the sample size, this also increases, and if this increases, that gives you a downward shock to the variance of beta j. So, that means that gives some counter impact on the VIF, and as a result of which severity of the multicollinearity goes down as you increase the sample size. The other thing also that happens when you increase the sample size, as I told you earlier, that suppose you are working on a consumption function, which is basically a function of income and wealth. So, what basically you need in your sample, the two variables income and wealth, not to be correlated, because while specifying the model, the theory suggests in the population these two variables are not correlated. So, when you get a sample, as you increase the sample size, there is a higher probability that you will collect information from those individuals in your sample. There are individuals with high income but low wealth, at the same time high wealth but low income. So, these two things you can achieve by increasing the sample size, right. Now, today we will talk about another solution, solution number 2, but please keep in mind all these solutions what we are talking about, they have some benefit, some cost as well. So, we do not know which particular solution will work in which particular context. That is why no particular measure can give you an universally true kind of solution. So, that is the reason we are discussing so many alternatives. Otherwise, we would have stopped our discussion only by here by increasing the sample size, because increasing the sample size also has its own cost. It is not always possible to collect a bigger sample without involving your so much of time, energy, even in terms of monetary costs, right. So, if it is possible, you can increase the sample size and your severity of the multicollinearity problem will come down. If it is not possible to always increase the sample size, we need to think about the other ways by which you can actually reduce the severity of multicollinearity. And the second solution is the transformation. transformation of variable. And here we will first discuss two things. Within the transformation of variable, this is 2a, which says that you can reduce the severity by taking the first difference. First difference. How? We will explain. Let us say that your model is yt, you have a time series data on alpha plus beta 1 x 1 t plus beta 2 x 2 t plus beta 3 x 3 t plus ut, where let us say yt is basically your consumption at the macro level, consumption expenditure at the macro level. Then x 1 t is, let us say, GDP per cap, GDP of the country, GDP, and then x 2 t is x 2 t is, let us say, your let us say this is population. Let us say that I have only two variable here. Okay, I have income, which is given by GDP, and also population. These are the two factors that determines the consumption expenditure of the country, and we assume that GDP and population, they are highly correlated. Okay, they have high pairwise correlation. Now, how will you apply the first difference? If the relationship holds true for the tth period, obviously the relationship holds true for the t minus 1th period. That means the same equation we can write for the t minus 1th period. So, what will happen if I take the equation like this? This would become alpha plus beta 1 x 1 t minus 1 plus beta 2 x 2 t minus 1 plus u t minus 1. And then what you do, you take this yt minus 1 equals to beta 1 x 1 t minus x 1 t minus 1 plus beta 2 x 2 t minus x 2 t minus 1 plus u t minus 1. All right. So, if you do so, then what happens? If x 1 t and x 2 t are correlated, there is no reason to believe that x 1 t minus x 1 t minus 1. So, let us say that this is delta y t equals to beta 1 delta x t x 1 t plus beta 2 delta x 2 t plus this would become u t minus u t minus 1 plus delta u t. So, that means what we are saying, that just because x 1 t is correlated with x 2 t, we cannot say that delta x 1 t would be correlated with delta x 2 t, and even if they do so, the severity of the correlation would be much lower when you take the difference, right. So, that means by doing the transformation, if you have a time series data, when you take the first difference, then severity of the multicollinearity problem goes down. but as I said, every measure has some cost also. What is the cost? The cost here, if this ut and ut minus 1, actually they may show you some kind of correlation. So, if your original variable does not show any kind of serial correlation, the moment you take the difference, then that may show you some kind of autocorrelation problem. So, autocorrelation problem may arise in this first difference when you assume this ut does not show any kind of autocorrelation. That is the problem with the first difference. And also, if you see, our original interest in this model was to see the impact of x1t on yt, but ultimately after transformation what we are getting is actually impact of delta x1t on delta yt. Okay? That is the model we have derived. So, this is the cost involved with the first difference method. Then under transformation, this is 2b I would say, and this transformation is, let us say, taking ratios, taking ratio. So, your model is yt equals to beta 1 alpha plus beta 1 x 1t plus beta 2 x 2t plus ut, where x 1t is GDP and x 2t is population, and over a period of time GDP and population, they show some kind of linear trend. So, there is a chance that GDP and population would be highly correlated. So, what you do to overcome that, you divide both sides of the equation by x 2t. So, what you will get? You will get yt by x 2t equals to alpha into 1 by x 2t plus beta 1 x 1t by x 2t plus beta 2 plus ut divided by x 2t. So, that means after this transformation, what I am saying, that consumption per capita is actually a function of the, what is this? This is your consumption per capita. Consumption per capita is actually a function of, this is GDP. So, this is GDP per capita. So, instead of running the regression in its absolute form, you are basically running the regression on per capita form, which makes sense. Okay? So, you can also transform some of your variables in ratio form, so that I am not losing any information, because my information on population is also there in the form of consumption per capita and here GDP per capita. But what is the cost here? The transformed error term, which is ut by x 2t, this ut by x 2t may exhibit heteroscedasticity. We have not yet discussed heteroscedasticity, but for the timing, just remember, this means that error variance is not constant. So, to solve one problem, you have ended up with another problem. You are trying to solve multicollinearity problem, but after transformation, you may end up with heteroscedasticity problem. because here ut is also divided by x2t, the population, right. So, if your original variable ut is homoscedastic, then the transform variable may show you heteroscedasticity. That is actually the cost of transforming this variable in this format, okay, cost of taking the ratios. So, we have to again carefully think that whether to apply this method or not. Right. And then third solution, dropping variable. So, generally we think that whenever some variable is correlated with the other one, we will drop one variable and keep the other one. But here what is the suggestion? The suggestion is, if the variable is theoretically justified to be included in the model, dropping would lead to model misspecification. So, you cannot drop a variable when the variable is theoretically justified to be included in the model. For an example, we can say that consumption is actually a function of both income and wealth. So, even though they are highly correlated with each other, income and wealth both are theoretically justified to be included in the model. So, I cannot drop neither income nor wealth. What is the solution? You might have to increase your sample size. So, it is not possible. So, dropping is not possible when it is theoretically justified. If variables are added on ad hoc basis, then dropping is okay. So, you do not have a theoretical justification, you have simply included many variables, and now you see some of the variables are intercorrelated. So, you drop one or those variables, right, and keep the other one. So, it all depends on whether there is any theory behind this or not. Okay. So, dropping the variable will work in this way, right. And then the fourth solution is combining cross section with time series. So, if you can do so, then you may combine cross section with time series and get a panel data. So, in panel data, the severity of the multicollinearity problem goes down. That is also another solution, combining cross section with time series data. Okay. And fifth is applying factor analysis or principal component analysis. Here the idea is, let us say that you are trying to estimate what are the factors that determine the ways people adapt to climate change, right. So, that means your dependent variable is adaptation strategies, which is a function of, let us say, your income, then assets, and then your education, then your social capital, then your age, male, female, so on and so forth. There would be many factors that determines the ways people adapt to climate change adaptation strategies. Now, these independent variables, income, asset, education, social capital, so many of these variables, they show intercorrelation. Then what you do? You apply principal component analysis here to identify some of the principal component out of your n number of such independent variables. Okay? And then you construct some kind of index. Some kind of index, if you apply here PCA or factor analysis, principal component analysis, PCA or factor analysis FA, then you will get some kind of adaptive capacity index. Adaptive capacity index. So, instead of using all the variables, or you will apply principal component analysis or factored analysis. Here we will identify the important factors out of those, and then we will construct some kind of index. This is also another method of solving the multicollinearity problem, right, multicollinearity problem. So, depending on the situation, depending on your data set, we have to think about which particular method to apply and to solve the multicollinearity. Now, what we will do? We will take one hypothetical data set and we will see what type of consequences may arise due to the multicollinearity problem. And this is a data. Look at the data set. This is a hypothetical data on consumption, income and wealth, right, consumption, income and wealth. And what I said, if you remember that when you import the data before estimating the model applying regression, what you actually do immediately after incorporating the data, you just look at the pairwise correlation. And what is the command? This is core, CORR, then income and then wealth. Now, look at the intercorrelation. The intercorrelation between income and wealth is actually 0.9990. So, that means almost 1, almost 1. So, there is a high degree of multicollinearity. So, if you estimate the model in presence of multicollinearity, what will happen? Rig consumption, income and wealth. Now, look at what are the consequences of multicollinearity as we discussed yesterday. Your income variable is insignificant. What is the p value? 0.290. If you multiply that by 100, that would become 29. So, that means I cannot say that the variable is insignificant. What about wealth? Wealth is also insignificant because it is p value is 0.615. So, that means you have estimated a model including income and wealth, but ultimately both the variables are insignificant, right. Not only that, you see the sign of wealth variable, it is not only insignificant, but the sign what you are getting is negative, which is very difficult to justify. How come wealth could have a negative impact on the consumption, which is a very difficult thing to justify, because our theory says that as wealth increases, that also gives you some positive impact on your consumption. Here it is coming totally different. So, you can now understand the severity of the multicollinearity problem. Variables are insignificant and they are coming up with unexpected sign also. And then when you look at the R square, the R square is 0.9635. That means your model explains 96.35% variation in consumption, but none of your variable is significant. How is it possible? Who is explaining them? And there comes the significance of our F test. If you remember that even though variables are insignificant individually, the model becomes overall significant. So, individual insignificance, but overall significance of the model, as I told you earlier, is a classic symptom of multicollinearity. Here both the variables are insignificant by their individual t statistic, but the variable is significant overall. So, that means F statistic should only be applied in this context to see whether the model is significant or not. Individual t statistic will mislead you in the presence of multicollinearity, because these t statistics, they are not the actual one, they are the artificial t statistics as a result of the variance inflating factor. That means the standard error got inflated in presence of multicollinearity, and as a result of which this T1 and T2 they have become insignificant. So, that means here what is happening, once again I will apply the diagram. Let us say this is T1 distribution, this is T2, and both are insignificant, but T1 and T2, just because both are insignificant, we cannot say that model is also overall significant. That means T1 and T2 should not map with F. Why? Because you are drawing the sample, you are drawing the distribution from the same sample, and that is why this F gains extra significance in this context. Okay? So, F gives you overall significance of the model. Overall significance of the model. And what is the value of F? Look at the value of F. F value is 92.40 and probability P, that means P value associated with that F is 0.0000, which is highly significant, okay, which is highly significant. That means what is happening here in the context of multicollinearity? In the context of multicollinearity, if you look at your, let us say, I will draw you an interesting diagram. So, let us say this is the distribution of beta 1 and this is beta 2. Now, if you look at the confidence interval of beta 1 and beta 2, look at first the income. The confidence interval 95% is minus 1.00 to 2.88. Let us say this is minus 1.00, this is 2.88. Okay. This is the interval 95%. Now, this 95% confidence interval of beta 1, 95% confidence interval of beta 1 captures 0. And what was our null hypothesis? Null hypothesis beta 1 equals to 0. Okay. Similarly, the null for beta 2 is 0. So, 95% confidence interval captures 0. So, that means we do not reject the null. Do not reject null. Similarly, if you look at the 95% confidence interval for beta 2, what is happening here? Look at the wealth, this is minus 0.23 to 0.14, minus 0.23 to 0.14, minus 0.23, minus 0.23, sorry, minus 0.23, let us say minus 0.23, let us say this is minus 0.23, and what is the value of this is minus 0.23, and what is the other one? That is minus this is 0.14. Let us say this is 0.14. So, again if you take this 95% confidence interval for beta 2, that also captures 0. Look at this, it is your 0, 0. So, 95% confidence interval of beta 2 also captures 0. Okay, that also captures 0. And what is the solution then? Do not reject H naught. So, as a result of which both income and wealth, they become insignificant. Okay, insignificant. But what about the joint significance? Okay, joint confidence interval, if you apply, they have basically an elliptical shape. This is the joint confidence interval. That does not capture 0.